Alright guys, welcome to Information Representation. This is the first unit for the A or AS level computer science exam. In this video, we're going to cover the 4 sections in this unit. That's going to be data representation, which is working with binary numbers, graphics, sound, and then compression. Let's get started. So the first topic we're going to cover here is expressing data amounts, and this is relatively straightforward. So basically, one thing to remember is that 1000 bytes is going to be 1 kilobyte. 1000 kilobytes is going to be 1 megabyte, 1000 megabytes is going to be 1 gigabyte, and so forth. And for some context, 1 byte equals 8 bits, and each bit is going to be like a 1 or 0, so a single binary value. And we'll go more into binary values pretty soon here. So kilo, mega, giga, tera. Those are really what you need to know, along with the definition of byte and bits. Now, one other way of expressing values that we do have is this kiba, meba, giba, teba sort of scheme right here. And the idea here is that while a single kilobyte might represent 1000 bytes, here a single kilobyte represents 1024 bytes. So, for example, right here, if we have, so basically 1000 bytes. Well, actually, let's say we have 5 kilobytes. Okay, 5 kilobytes. That's going to be equal to 5000 bytes. But if we have 5 kilobytes, I think it's like written something like this. I'm actually not sure. 5 kilobytes, that's going to be equal to 5120 bytes. So it kind of makes sense in a way because 1024 is a common sort of quantity that's used to express, for example, values or amounts of RAM. And it's often used in computing. But at the same time, like I had never seen this way of expressing values until I started making this video. So this is going to be more common in real life, but you need to know both for the A-level exam. Now, just probably one key difference to remember when distinguishing between these is that these 1024, these sort of multiples of 1024 are going to have the by like sort of not values, but it's going to have this like by sound or by the bi letters in every term, right? So kiba, meba, giba, teba, etc., which doesn't really exist here. So now to kind of illustrate this, let's take a look at an A-level example. So right here, first we've got 8 bits, and we know 8 bits is going to be 1 byte, so we can just go ahead and match this up right here. Next we have 8000 bits, and we know it's going to be 8 bits to 1 byte. So that means that this is going to be 8 bits times 1000 bytes, right? Or it's really just going to be, this is 8 times 1000. Let's see, 8 bits times 1000, right? And so that's going to end up being 1000 bytes, or sorry, 1000 bytes, which is equivalent to 1 kilobyte. Similarly, right here we have 8 bits, but 8192 represents 8 times 1024. And 1024 represents, so if we're talking about 8 bits times 1024, all of this together is going to end up being 8 kilobytes, or sorry, 1 kilobyte. So 8 bits is 1 byte, and we're going to have 10,024 of them. So we're talking about 1 kilobyte right here. So this one's going to match up to this one right here. Next we have 1000 kilobytes, and 1000 kilobytes is just going to equal 1 megabyte, and we have 1024 megabytes, and that's going to be 1 gigabyte, not a gigabyte. So really, if you go back here, it's almost like a linguistic thing, but we have kilo, mega, giga, tera, and we have kiba, meba, giba, and teba. So right here, it's just really that by that's making the difference between the two ways of expressing data amounts. It's kind of weird and semantic. They both have their place, but the one on the left, the kilo, mega, giga, tera, is obviously the most, I would say, the most common way of expressing data amounts. And I think we got the right answers. So next what we're going to talk about is binary. And binary is important because this is the language of the CPU and modern computing. So whenever we write a programming or we write some code in a programming language and we have it execute in our computer, that code is being converted to binary, which is essentially a series of ones and zeros. And binary itself is a base 2 method of expressing values. And this is in contrast to the normal decimal values we use, like 1050, which is as expressing values in base 10. And when I illustrate how binary works, it'll be a bit clearer as to what I mean by base 2. This is important to know because, again, this is a language in which the CPU interprets our code and in which data inside a computer is generally going to be transferred. And that's the reason why the A-level saw it necessary for us to learn about binary and binary arithmetic and how to convert to binary. So to kind of illustrate how that works, let's go ahead and just take a look at an example that's already been worked out. So here, convert the 8-bit binary number 000111010 into denary. Now, denary is going to be the type of numbers that we are used to using. So the numbers we use in everyday life, for example, 26, 359, etc. One thing to keep in mind about binary is partly because it's base 2. Again, we'll explain what base 2 means here soon. The only possible values in a binary number are going to be either 0 or 1. Now, to kind of just get into, really to demonstrate how this works, we just need to work through a problem. So we have 0, 0, 0, 1, 1, 0, 1, 0. Now, we're going to start from the right and work our way to the left. Now, the first digit on the right in a binary number, so this one right here, is going to represent 2 to the power of 0. This is going to represent 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7, and so forth. We only have 8 values here, but if we were going to have a larger number, the subsequent digit would represent 2 to the power of 8, 2 to the power of 9, etc. So these are representing these values. And so for example, that means that right here we're representing 1, 2, 4, 8, 16, 32, 64, 128, 256, and so forth. Okay. Now basically each one of the values in this particular binary number represents the number 2 to the power of whatever digit it is. So this one right here represents 2 to the power of 0 because this is like the 0th digit. Next one, this one here is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, etc. And that's why we call this a base 2 number. Now, if we look at a denary number, which is base 10, right? So let's say we have like 1, 3, 5, 6, okay? Actually, before we get to denary, I'm just going to go ahead and show you how we would get the actual value, how we would convert this to denary, right? So right here we have a 0, so we're not going to do anything. Okay, so here we have a 0, so we're not going to do anything. Here we have a 1, so 2 is going to be part of the value that we're calculating. Right here we have 0, so we're not going to do anything. Here we have 1, and 2 to the power of 3 is 8, so we're going to add 8. Right here we have 1 as well, which represents 2 to the power of 4. So we're going to add 16. And that's actually it. These are 0, 0, and 0. So these aren't going to be part of the subsequent denary value. So the total value of this number right here, as we've calculated, would just be 26. Okay. Now that's how we would calculate the denary value or the regular value of a base 2 number. To kind of give you some context as to what base 2 means and why I keep using this term, I'm going to show you what base 10 means. Now base 10 is just like our normal way of expressing numbers. So 26 is base 10 and denary is going to be base 10. So if we like really look at how a base 10 value works, or like a regular number works, let's say we have the number 1356. Okay. Actually, I'm going to separate these a bit so I have some room to work around each value. So let's say we have 1356 right here. All right. So the way this works is the first digit, starting with 6, is going to represent 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3, and so forth. So if we really want to get the value of this number without just knowing that it's 1356, what we'd be doing is we'd be doing 6 times 1 plus 5 times 10, because this is 1. So this represents 1, 10, 100, and 1,000. Plus 3 times 100, right? Plus 1 times 1,000. And these values right here just represent these right here, 6, 5, 3, 1, multiplied by their place, multiplied by 10 to the power of 3, 10 to the power of 2, 10 to the power of 1, 10 to the power of 0. Similarly, right here, if we go back here to our binary number right here, we had 0 times 2 to the power of 0, plus 1 times 2 to the power of 1, plus 0 times 2 to the power of 2, plus, what is it, 1 times 2 to the power of 3, plus 1 times 2 to the power of 4, and that was pretty much it. And then the sum of that is what's going to give us our value. So hopefully that kind of gives you an understanding of what base 2 means in the context of actually doing these calculations. And this is just the first example of how to calculate from binary to denary. We'll see more examples like this. Now, one thing to keep in mind as well is that, for example, in a base 10 number, we have 10 possible values for each digit, right? So if you have one, let's say we go back to 1,356, for example, for the first decimal, we could have any value from 0 to 9. That's because it's base 10. We can have 10 possible values. However, for base 2, it's base 2, so we have 2 possible values. And that's going to be either 0 or 1. So again, hopefully that's a good primer as to how binary works. Let's move on to some examples. Okay, so the first example we're going to look at right here is how to convert this binary number to this right here. So right now we're just focusing on converting binary numbers to denary numbers, right? So we're going to have 1, 1, 1, 0, 1, 0, 0, 1. So usually the easiest way to start out is just by writing out our base 2 exponents, or base 2 values. So by that I mean we're going to write 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. And honestly, for doing this, I think it makes a lot of sense to memorize what each of these values represents. So if you haven't already done it, I mean, I think that a lot of people probably at least know the first couple. This is going to be 1, 2, 4, 8, 16, 32, 64, and 128. Honestly though, it'll just make your life a lot easier if you memorize these. So we're going to look at in this value where we have 1, and we're just going to add those values together. So 2 to the power of 0, we've got 1. So we can do 1 times 1, right? 1 times 1. For 2 to the power of 1, we have 0. For 2 to the power of 2, we have 0. For 2 to the power of 3, we have 1. So we can go ahead and do 1 times 8. For 2 to the power of 4, we have 0, so we're not going to do anything. Now next we can do 1 times 32, because we do have a value for 2 to the power of 5. So we're adding all of these up. And then 1 times 64 for the same reason. And then we can do 1 times 128 for the same reason. And so we're just going to end up with 1 plus 8 plus 32 plus 64 plus 128, which is ultimately, so that's going to be like 40 plus 64, which is like 124, so 125. Hold on. So 40 plus 64 is going to be 104, right? Plus 1 is 105, and 105 plus 128 is going to give us 233, which is our answer right here. Okay. Now, what I'm going to do next is I'm going to just solve our next example, which is right here. I just think that seeing a lot of examples is super important, which is why we're going to do this. And so we're going to start with 1, 0, 0, 1, 1, 0, 1. We're going to go through the same process. Like, once you understand how this process works better, I mean, you can cut through a few steps and you can probably get this done more quickly. But again, this is for illustration purposes to just show you like, okay, this is how this process works. All right, so I actually think I missed a 0 here though. So that's going to be 0 and then 1. So, okay, so now we're just going to go ahead. Again, I'm going to go through the same slow process: 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. But it looks like our 1s are going to be 2 to the power of 7, 2 to the power of 3, 2 to the power of 2, and 2 to the power of 0. So we can actually, I mean, we're multiplying by 1 every time. This isn't like a denary or decimal number. So we can go ahead and just do 2 to the power of 7 plus 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 0. Remember, 2 to the power of 7 is 128, so we're just going to have 128 plus 8 plus 4 plus 1. And so 128 plus 12 is going to give us 140. So we're going to have 140 plus 1 equals 141. That's how you go ahead and do that. One thing I do want to kind of go over before we do move on is also how to go the other way. So these are converting from binary to denary, right? So we're going to look at this a little bit more later on, but I still want to kind of just give you an understanding of how that works because that's something you might have to do on the A-level exam. So I'm going to go ahead and just erase this example right here. And next, what I'm going to do is I'm just going to say, let's say we want to go from 233 to what our answer was right here. So we're going to go the other way, right? So what you want to do first is you want to start out by filling in. The idea is that you want to have the fewest possible ones in your value. So what we're going to do is we're going to start by filling in the biggest values that we can fit into our number. And I'm going to give you an example of this. So generally, the highest possible number we can have with 8 bits, and this is 8 bits, right, is going to be 255. Okay. So that's going to be like the highest possible number that we can represent with our 8 bits, right? And part of the reason for that is because 2 to the power of 8 is just going to be 256. Okay. So if we have 233, we're going to start. So I'm just going to go ahead and write out our possible decimals. So if we can have a maximum of 8 bits, that means we just need to write out 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7, and fill them in accordingly. And I'll just write our numbers, especially like the first ones. It's actually pretty easy because they just go by multiples of 2 downwards from there. Okay, so we want to fill this in starting with the largest possible values that can fit into our given number. So we're going to start with, okay, we have 128. Does that fit into 233? Yeah, that does. So you can put a 1 there. If we do 233 minus 128, we're going to end up with like oh God, I hate math. We're going to end up with 105, right? Because 105 plus 128 equals 233. So now with the subsequent numbers in this value, we need to account for 105. We've already accounted for 128, so that's out of the picture, but now with the rest of these values, we need to get to 105. So we can say, does 64 fit into 105? Yeah, it does. So now we can subtract 64. And then we've got about, I want to say like 41 left over. So that means with the subsequent values, we need to account for 41. Now does 32 fit into 41? Yeah, it does. So we can fill that out. 32, and then we've got about 9 left over. Does 16 fit into 9? Nope, 16 is bigger actually. So we're just gonna put a 0 right there. Does 8 fit into 9? Yeah, it does. So we can put a 1 right here, and we can subtract 8 from 9, and we've got 1 left over. And does 4 fit into 1? No, it doesn't. Does 2 fit into 1? No, it doesn't. Does 1 fit into 1? Yep. And we end up with 0. And we'll probably look at some other examples of this, but that's just an example of how you go from denary to binary, not necessarily from binary to denary. Anyways, let's move on. Okay, so let's take a look at an A-level example here. So convert the unsigned binary integer into denary. Don't worry about the unsigned part. We're going to get to that later, where we look at binary integers or binary values that do have signs. But basically the idea is we want to convert this to denary. And this is a larger example than we've seen before. It has more bits than we're used to. We're going to go ahead and break it down. So I'm going to go ahead and write this out with some space between the digits. So I'm going to go ahead and write out 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0. Okay, we're going to go ahead and write out our powers. So we're going to write 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 4, 5, 6, 7, 8. So the reality here is that actually we have, these aren't going to really give us any values because they're all 0. And the largest binary value we're going to have, or the largest binary digit, is going to be this one right here. So what we can do, we're going to have 2 to the power, well actually let's go ahead and write out the values for this. So that's going to be 1. Actually, we don't even need that. We're only going to write it out for the values that have a 1 attached to them. So 2, 4, 16, 64, 128, 256, right? So let me just make sure. Okay, cool. So that means to get our value, we can do 256 plus 128 plus 64 plus 16 plus 4 plus 2. So, okay, 256 plus 128 is gonna be 284, I wanna say. Or sorry, 384. Anyways, so the answer is gonna be 470, right? And again, this is slightly larger than what you're used to, but it helps a lot to really be able to remember what all of the different powers of 2 are, because then you can just go through this process much more quickly than trying to like use a calculator or try to, you know, just do it all in your head without actually just memorizing this. Okay, so now what I want to do is take a look at some additional examples of converting from denary to binary. And we're going to start by filling out this chart. We're going to start with actually a very small denary number. So what I want to do is start with, let's say, 42. And we're going to fill in this chart right here with our matching binary value. So the first thing we need to do is we need to look at, so I mean, first of all, each of these numbers represent a particular place in our base 2 number. So really, this would be the equivalent of a decimal place if we were talking about a regular denary decimal number. But basically, this is going to be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. And that's what this all represents. Now, what I want to do first is I want to look for the biggest value that will fit into this number right here. And we see that 128 and 64 are both bigger than 42. So those are not going to have, those are not going to have a 1 value. Those are just going to be 0. Because we can't, 2 to the power of 6 or 2 to the power of 7 are not going to be used to represent 42. But 32 can fit into 42. 32 is smaller. So we can put a 1 right there. And that's going to account for 32 out of 42. So if we do 42 minus 32, we have 10 left over. So the rest of these digits need to account for 10. So now what we're going to look at is from what we have left. So we've got everything from 2 to the power of 4 to 2 to the power of 0. What's the biggest number that can fit into 10? It's not 16, so we're going to put a 0 there, but it is 8. So we can go ahead and put a 1 here, and we're going to subtract 8. And now we have 2 left to account for. And 4 is too big, but 2 is just right. So we're going to have 0, then we're going to have 1, and then if we do 2 minus 2, we have 0 left. There's nothing more to account for. So we can just put a 1, or we can just put a 0 right here. And this is going to be our equivalent binary value. Now, a lot of times, different questions will ask you for an 8-bit value, or 16-bit, or 12-bit. So this is going to be an 8-bit value. So if you write 0, 0, 1, 0, 1, 0, 1, 0. This has 8 digits, so it's going to be an 8-bit value. Technically, we don't really need 8 bits to represent this value. We only need 6 bits. So we could represent it this way, but it all depends on what the question is going to be asking you. Anyways, I think examples is really important here, so let's go ahead and look at a few more examples. So the first thing I want to do is I want to convert 168 to binary. So I'm going to start, we don't have the luxury of a chart like we did before, so I'm going to start by just writing out some of our different, I guess, places. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. And I know that the biggest value that's going to fit in here is going to be 2 to the power of 2 to the power of 7, which is 128. So I only need to go that far. So 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. 2 to the power of 8, 2 to the power of 8 is 256, and it's bigger than this one, so there's no reason to really include that here. But we know 2 to the power of 7 is going to be 128, and 128 does actually fit into 168. So we can go ahead and do 168 minus 128, and we're left with 40. and we're going to put a 1 right here. So our next value right here is 64, but 64 is too big to fit into 40. So we're going to go ahead and put a 0 right here, and we're going to move on. Now our next value is 32, and 32 is small enough to fit into 40. So we can go ahead and put a 1 right here. We can do 40 minus 32, and we're left with 8. So I'm going to go ahead and just write these out just for clarity, right? So 8, 4, 2, and 1. Now we have 8 left over. 16 is too big, but 8 is just right. So we can go ahead and we can write 1 right here and fill in zeros everywhere else. And yeah, so like if you do 8 minus 8, we're going to end up with 0, and so we're good to go. And that's it. Now let's just take a look at one more example. And so let's take a look at 83, and we're just going to go through the same process really. I'm actually just going to write out everything from, I mean, maybe I shouldn't have like erased all of that, right? But we're just going to assume that all of these are 8-bit answers. So I'm just going to write out up to the power of 7, all right? And so 83, remember 2 to the power of 7 is 128, and 83 is actually too small. Like 128 is not going to fit into 83 because 128 is too big. So we're going to put a 0 right here, and we're going to start with 64 because 64 does fit into 83. And 83 minus 64 is going to be like, what is that? 19? Sorry, I'm terrible at math. Yeah, 19. So we can go and put a 1 here, and we can do 64 minus, or we can do 83. Well, we actually already did 19. We have 19 left over, and that's what we want to account for. So 32 is going to be too big. 32 is too big for 19 to fit into 19. Next, you've got 16, which is actually the right size to fit into 19. So we can go ahead and put a 1 here. We can do 19 minus 16, which equals 3. And that's, now we just need to account for 3, right? We can go ahead and put a 0 right there. So next we have 8 to the power of 3, and that's too big to fit into 3. So we'll put a 0 right there. We have, or next we're going to have 4. Oh, did I miss something? Oh, I missed 2 to the power of 2, my bad. So we're going to have you should have 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. Anyway, so we're going to have 4, which is again like too big to fit into 3. So we're going to go ahead and put a 0 right there. And next we have 2 to the power of 1, which is 2, and 2 does fit. So we can go ahead and put a 1 right there. And then we can do 3 minus 2 equals 1. We just have 1 left over, which is perfect because 2 to the power of 0 is 1. So we're going to have 1 right there, and this is going to be our answer. So as you can see, a lot of this is really accounting, with the idea being that we start with the biggest value in the number of bits we have available. So we just look right here at our powers, assuming this is an 8-bit number, and we find the biggest value that can fit into 83. Now, if we had a value like, for example, 272, we would want to start at 2 to the power of 8, which is equal to 256, because that's the maximum value that would fit into 272 from our different, from the different values that are available to us based on the powers of 2. Similarly, if you had something that was bigger than 512, 2 to the power of 9 is going to be 512. So if you had like 572, our first value is probably going to be right here. This is probably going to be a 1. But I decided to work with smaller numbers here just to kind of keep things simple. Anyways, let's move on. So what we're going to do now is look at hexadecimal, right? And hexadecimal is kind of an extension of, well, when we were working with hexadecimal, we're basically going to be working with a concept that's an extension of both the binary and denary numbers that we worked at before. Because hexadecimal is just another way of representing values, but it does so as base 16. So for example, if we have a binary value that's like 1, 0, that's 1, 1, then this represents 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3, right? If we have a denary value that's like 5, 6, 7, 3, this is 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3. Now if we're talking about a hexadecimal number, remember this is base 2, and this is base 10. Hexadecimal is base 16. Now this means that, first of all, we have 10 possible digits, right? 0 through 9. With base 2, we have 2 possible digits, which is 0 or 1. Now, hexadecimal things get a bit weird. So we have 15 possible digits, or rather 16 possible digits. And that's going to be like 0 through F. And we'll kind of go through a little bit more of like what this means. But basically, like when we represent values, we might have something like 3F, right? And this is going to be 16 to the power of 0 and 16 to the power of 1. Now, 0 to 9 is going to be just the same values we're used to, right? So, but then 10 is going to be A, 11 is going to be B, 12 is going to be C, 13 is going to be D, 14 is going to be E, and 15 is going to be F. So F is like theoretically the highest digit we can have. So if you have the value 3F, then we know 16 to the power of 0 is 1. So we're going to have 15 times 1. And we know that 3 is just going to be 3. So we're going to have 3 times 16. And then we would add those values up to get our denary equivalent, right? So 3F would be equal to 15 plus 48, which is going to be 63. Like that's going to be our equivalent value for 3F. Now, hexadecimal is used to more efficiently represent large binary values. It represents colors. It's used extensively to represent memory addresses, also MAC addresses, which are used in networking, which you'll cover in the networking topic if you haven't covered that yet. So it is used pretty extensively, and that's the reason why it's covered in this curriculum. Now, one thing to keep in mind, and one reason, like I just want to really quickly demonstrate in a more, I guess, literal way why we use base 16. So, okay, let's say that we have 1, 0. Well, actually, let's see like, yeah, let's look at our places. So we have 2, 0, 2, 1, 2, 2, and 2, 3. Okay. So if we had these values, the maximum value you could represent would be this 1, 1, 1. That's basically going to be 8 plus 4 plus 2 plus 1. And that's going to be 8 plus 7, which is 15. Okay. Well, right here, so for example, with one hex digit, the maximum value we can represent is 15, right? The highest value we can have is F. F represents 15, and 16 to the power of 0 is 1. So with one hexadecimal digit, we can represent the denary quantity 15. With 4 binary digits, we can represent the denary quantity of 15 as well. So a lot of times hexadecimal digits are used to represent binary values because each hexadecimal digit can be representative of 4 binary values. So for example, if we had a binary value with 16 digits, right? We could represent that in 4 hexadecimal digits. And this basically allows us to more efficiently and a lot of times more clearly represent large binary values. Hence the reason why we use hexadecimal in place of binary. Now to further solidify our understanding of hexadecimal, which may be like a new concept to you, we're going to go ahead and look at a few more examples. So right here, first of all, this is a chart that shows us how decimal values are represented in hexadecimal. So as you can see right here, we have F representing 15, E representing 14, D representing 13, and so forth. And our decimal values are represented in hexadecimal by pretty much what we'd expect. So we're going to look at this value right here, which has 3 digits. So we have 2A5, right? And 2 represents 2, A represents 10, and 5 just represents 5. So this is going to be 16 to the power of 0, 16 to the power of 1, and 16 to the power of 2. So to get the equivalent denary value, or decimal value, which we're used to, what we could do is we could do 2 times 16 to the power of 2, which is 256, plus, it's going to be, A is 10, so it's going to be 10 times 16 to the power of 1, which is a 16, plus 5 times 16 to the power of 0, which is just 1. So really we'd have 512 plus 160 plus 5, and that's going to end up giving us 677, as we can see in our example right here. So this 16 right here means it's a base 16 value, or hexadecimal, and this 10 right here means this is a base 10 value, or decimal, which is the kinds of numbers that we're used to. Okay, so as I said before, we're going to go ahead and back this up with some additional examples. So right here we have 3b, right? And what I want to do is convert this to a regular decimal value, which we're used to. So this is going to be, this first digit is going to represent 16 to the power of 0, and this is going to represent 16 to the power of 1. So we can go ahead and get our denary equivalent by doing 3 times 16 to the power of 1. And we can add this to b, which remember, a is going to be equal to 10. And so that means b is going to be equal to 11. So it's going to be plus 11 times 16 to the power of 0. So 3 times 16 plus 11 times 1. So it's going to be 48 plus 11, which is just going to give us our answer, which is 59. Now we're going to look at a slightly bigger value, which is going to be 18e. So e is actually going to be equivalent to 14, right? So we've got 18e right here. And again, this is going to represent 16 to the power of 0, 16 to the power of 1, and 16 to the power of 2. Now 16 to the power of 2 is 256. So we're going to have 1 times 256 for this value right here. We're going to have 8 times 16 to the power of 1, which is just 16 for this value right here. And then we're going to have, so e is going to be 14 because f, our biggest value, is 15. So we're going to have 14 times 1 right here because 16 to the power of 0 is 1. So we're just going to have 256 plus, I want to say, let's see, 80, I guess it's like 128 plus 14, which should be equal to 398. I really hope it is. Because again, I'm terrible at math. Anyways, that's how you go about solving that problem. Okay, so now that we covered how to convert from hexadecimal to denary values, the natural next step is going to be converting from denary to hexadecimal. And this roughly follows a similar process to what we saw when we were converting from denary to binary. Now these types of questions aren't very common, but I thought it would still be useful to go through the mechanics of how this works. So right here we have the number 495, and we want to convert it to hex. Now with 16 to the power of, now if we start with 16 to the power of 3, we can see that 4096 is the smallest value that we can have in this place right here. Because the smallest value we could have is 1, and 1 times 16 to the power of 3 is just going to end up being 4096. But that is much bigger than 495. 16 to the power of 2, the smallest value is going to be 256. Hence, this is a good place to start when going ahead and trying to convert to a denary value. So if we have 1 right here, that's going to be 256. 2 would be 2 times 256, which would be 512, which would be bigger than the number we want to convert right here, which is 495. So we can go and put a 1 there. And then what we can do is 16 to the power of 1. So if we do 256, we can do 495 minus 256, and that's going to give us like 243, yeah. So we still need to use this to account for 243. And the way we're going to do that is we're going to see what's the highest value that will go into 243. Now, it's probably going to be something like 16. Yeah, I think it's going to be, okay, so that's going to end up being probably 15 right here. 16 times 15 is just 240, unless I am very much mistaken, which is entirely possible. Because 16 times 10 equals 160, and then 5 times 16 equals 120. So that means that we can have an F right here. So this is actually going to be 0. We're going to have one F. So if that gives us 240, that means you've got 240 right here. So we can do 243 minus 240, which is going to be equal to 3. And then for our last place, we're going to have 16 to the power of 0. And to get 3, we just need to literally put a 3 right here, because 16 to the power of 0 times is 1, and 1 times 3 equals 3. So this would be our answer for 495 if you were converting it to hex. So naturally here we've got a few more examples to solidify our understanding of these concepts. So we have 480, and we want to convert this to hex. So we're going to go to 16 to the power of 2, 16 to the power of 1, and 16 to the power of 0. And typically you're not going to have a value that's going to be larger than 3 digits in hex on the exam at least. So we know that the smallest value that we can make with this is going to be 256. And that's going to be where we just have 1 right here, because 1 times 16 to the power of 2 is going to be 256. So if we have 256, then we can subtract that from here. She'll make that red minus 256. And that's just going to go ahead and give us, like, what is that? 224, right? If you remember from our last example, when we had 15 times 16 to the power of 1, that gave us 240, but that's too big to fit in here. But the next value we would have would be like 224 actually. So that means that instead of 15, we would just have 14. And if 15 was F, then 14 is going to be E. And actually 224 minus 224 is 0. So that actually just gives us our answer. Now, I think that was a pretty easy question. Let's go ahead and take a look at the next one. So kind of going through the same process, we're just going to go ahead and write out our places. So we're going to have 16 to the power of 0, 16 to the power of 1, and then 16 to the power of 2. Now, 256, which is the smallest value right here, is going to be too big for this digit. So we can just go ahead and get rid of this. And so 16 to the power of 1, like we know that 15 times 16 equals 240, and 14 times 16, or E times 16 to the power of 1, equals 224. And 224 does go into 232. So if we put E right here, that means we would have 232 minus 224, because 224 is going to be what E gives us. That's going to be 14 times 16 to the power of 1. And that's going to leave us with 8 to account for. So that means we're just going to have 8 right here, because 16 to the power of 0 times 8 is just going to be 8. Again, another simple example, but I think it gets the point across. So next, we've done denary to hexadecimal, we've done hexadecimal to denary. Now we're going to do hexadecimal to binary, and this is where you're going to kind of see how hexadecimal and binary can quite easily work together. Now the key thing to remember is that each hexadecimal digit represents 4 binary bits. So basically, let's say that we have a binary number like 11011. Actually, I'm going to write that. I mean, the thing is, when we look at binary numbers, we're going to be writing them in multiples of 4 because each hexadecimal digit represents 4 binary bits. So if you look at this one right here, we have 1011, and then we have 11. And again, because we're representing these in groups of 4, we're going to do 0, 0 right there. And that represents this number right here. So what we can do if you want to convert this to binary is we can see what binary digit would this make. Now, the way to do that would be basically to say, okay, well, what is the value of this? I mean, for me, the easiest is just to see what's the denary value, right? So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. This is going to be 8 plus 2 plus 1, which equals, let's see, it's 10, 11. And so that's just going to be equivalent to B, right? 11 is B in hexadecimal. If you look at this right here, 2 to the power of 0, 2 to the power of 1, that's just going to be 2 plus 1, which equals 3. So our representative hexadecimal value is just going to be 3B. Now, this might seem a little too simple, so let's go ahead and let's take a look at another example. So let's say that we have this value right here, and we want to turn this into hex. So we're going to start by splitting this up into groups of 4, right? So we're going to have 0, 1, 1, 0, the leftmost value, or rightmost value, and then 1, 1, 0, 1, which is going to be the leftmost value. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, this is going to be 4 plus 1, which equals, or 4 plus 2, which equals 6. And that can just be represented by 6 in hexadecimal. And this is just going to be, let's see, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. This is going to be 8 plus 4 plus 1, which is 13. And that's represented by D in hexadecimal. So our answer is going to be D6. Pretty simple, right? Now, if we want to go the other way, so if we have a hexadecimal digit like 92, and we want to turn that into binary, what we would just do is take each of these and write them in a 4-bit binary number. So like this would just be 0, 0, 1, 0, 2 to the power of 1, 2 to the power of 0, etc. And this would probably be, so we're going to start with probably 1, because 2 to the power of 3, and that's going to be 8, 0, 0, 1. And And so our value just end up being 1001, 0010. Now we're going to look at an actual A-level question, just so you can kind of see an example of how this would work in an exam type context. So convert the positive binary integer 1110010 into hexadecimal. The first thing I want to do is break this up into groups of 4, right? So right here, split this up into 2 groups of 4. We're going to have 0010 and 1111. And then I'm going to convert this to denary because it's easier. So to the power of 0, to the power of 1, to the power of 2, to the power of 3. I mean, this is just going to be the value 2, right? That's just equal to 2 in denary. And to the power of 0, to the power of 1, to the power of 2, to the power of 3. So that's going to be like 8 plus 4 plus 2 plus 1. It's like the maximum possible 4-bit binary value. And that's going to be 15. And so 2 in hexadecimal is just going to be 2, and 15 is going to be F. So the answer right here is going to be F2. And we're good to go. Okay, so the next concept we're going to be taking a look at is going to be binary coded decimals. And frankly speaking, I don't think this is that useful a concept, but it is an A-level exam, so we're going to have to learn it. And the idea behind this concept is the fact that if we have a decimal number like 260, each individual digit can be represented by a binary number, and basically putting those binary values together would give us that decimal number. So for example, at 260, we have the binary equivalent of 2, 6, and 0. And together, if these values are put together sequentially, that would give us our binary coded decimal value. So to see how this works, let's go ahead and take a look at an example. So this is from an A-level exam, and actually if we go back right here, we can see that each digit was represented by 8 bits. In this example, I know it isn't written here, it's written in a prior part of this problem, but basically each decimal digit is going to be represented by 4 bits. So that means we can break this up into 4 bits. So we have 1 bit right here, we have 1 bit right here, and we have another bit right here. And so this is going to be, so that's 1, 4, this is going to be 5. The decimal equivalent is going to be 5. So this is like 2, 4, the decimal equivalent is going to be 6. And this is just going to be 8 right here. So sequentially, we have 4 4-bit binary values. The equivalent of the first one on the left is 8, and then 6, and then 5. So our answer would just be 865. And that's basically how it works. So now we can take a look at another example, and this one's going to be similar to the previous one, and that each digit ought to be represented by 5 bits. Again, I know this isn't really written here, but it is written in a previous part of this question. So what we can do is we can take each one of these values and then convert them into a 4-bit binary value. So we'll start with 4. So 4 is just going to be 0, 1, 0, 0. 6 is just going to be, so I guess it's going to be 0, 1, 1, 0. And 9 is just going to be 1, 0, 0, 1. So we're going to go in the same order as the decimal number, and we're going to have 1, 0, 0, 1, 0, 1, 1, 0, and then 0, 1, 0, 0, and that's going to be our answer. And I think we did a good job. Okay, so now for our next value, or our next problem, it says a register stores the following binary number. State why the value in the register cannot be interpreted as a binary coded decimal. So again, in this one, we're going to go ahead and assume that each decimal is represented by 4 bits. As I said before, this won't necessarily always be the case, but it does seem like on most questions in the A-level exam, each digit is represented by 4 bits. But this one isn't going to work, and let's see why. So if we divide this into 4 bits, into groups of 4 bits, then, so first of all, right here, we're gonna have 1, 8, and, okay, so we're gonna have 1, and this is gonna be 4, and then we're gonna have 8, and that's gonna give us 13. And right here, we're gonna have, let's see, so this is gonna be 4, and this is gonna be 8, and this is gonna be 12. And both of these values represent numbers greater than 9, which means that we can't really interpret them as a binary coded decimal. In order for this to work, each of these 4-bit numbers would have to represent a value of 9 or less, because we simply, like, this isn't hex, right? Like, we don't have a E or F or whatever it is. So the answer here is that the denary value in each group of 4 bits is greater than 9, and that's all we could really say about that. So maybe I said earlier I don't really know what the applications are, but it turns out that there are some applications, even though I didn't know what they were. So first can be in financial and banking calculations. So we can often use these to give an accurate representation of decimal values in a more precise way. Electronic displays. So for example, if we were displaying something on a regular calculator, perhaps each one of the digits that are represented here would be equivalent to a single decimal, and that decimal value could be interpreted, be represented by a single binary value. So for example, 3 would be represented by a binary, 1 would be represented by a binary, and 4 and so forth. And then the individual display, so could interpret that binary value to display a number on the calculator accordingly. Also storage of date and time in the BIOS. So remember, the BIOS is that program that's stored in the RAM that allows us to turn on our computer and allows us to do really basic operations in our computer. And oftentimes, the storage of date and time in the BIOS is done using binary coded decimals. So financial banking calculations, electronic displays, and storage of date and time in BIOS are 3 applications of binary coded decimals. Okay, so now that we have an understanding of basically how binary numbers work, I want to look at another facet of binary numbers, which is how we can represent signed binary numbers. Now, there are 2 methods. One's called ones complement, the other's called twos complement. And here's how ones complement works. So basically, let's say we have a binary number like this. It's going to be 1, 0, 1, 0. Now, this is just going to end up being 2 plus 8, which is 10, right? Because that's going to be to the power of 0, to the power of 1, to the power of 2, and to the power of 3. Okay. Now, when we're using ones complement, a positive number is represented in the standard binary form. So if we have a positive, so if we want to represent positive 10, for example, if we want to represent this, then we can use 1, 0, 1, 0. Basically, our binary number is going to look exactly the same as it would in any of our previous use cases where signs weren't involved. But let's say we want to represent minus 10. Then we need to go through a process to convert this value, this number, to ones complement. And to do that, all we really need to do in ones complement is to invert it. So we're going to end up with 0, 1, 0, 1. So this right here would end up being equivalent to negative 10. Now, there are a myriad of problems with this approach. I'm not going to go into them now, but this is the reason why twos complement, which we're going to look at next, is actually more commonly used than ones complement. So now let's look at what twos complement is. Similar to ones complement, any positive number is going to be represented the same as in standard binary form. So if, for example, we have 10, and again, as we said, we can represent that as 1, 0, 1, 0 in binary, right? So this is going to be not only its standard binary form, but also its twos complement form. So nothing changes. But then, if you want to change it to negative 10, we need to go through a different process. Now, actually, this process involves converting to ones complement. So if we have 1, 0, 1, 0, we're going to go ahead and invert all these bits. And if you didn't get what invert meant, it basically meant that we should change all of the ones to zeros and all of the zeros to ones. So if we invert 1, 0, 1, 0, that's going to become 0, 1, 0, 1. And that's our ones complement form, but to make it twos complement, we need to add 1 to this value. And here's how this is going to look. So basically, we're going to do plus 0, 0, 0, 1. And we're just going to add those up. And we're going to do this the same way as you did addition in like the second grade, right? So first, we're going to add 1 plus 1 for this number on the top and on the bottom. And 1 plus 1 in binary is just going to equal 1, 0. And the reason for that is 1 is basically just to the power of 0, right? I mean, it's literally just a 1-bit number and represents to the power of 0 and to the power of 0. If we're adding those two up, then we just get 2. And 2 is represented as 1, 0, right? To the power of 0, to the power of 1. So this is going to be 1 plus 1 is 1, 0, but it's two digits. So we're going to put a 1 over here, and we're going to put the 1 all up here. I can't remember whether that's called carrying it over or whatever that's called, but anyways. Then we're going to add 1 plus 0 plus 0, which is going to be 1. And then we're going to have 1 plus 0, which is 1, and then 0 plus 0, which is 0. So that means that this now is going to be negative 10. We'll look at another example right here, down below. So right here we have this binary number, which is 110010. And this is going to be like 2 to the power of 1, 3, 2 to the power of 4, 2 to the power of 5. So this one is going to end up being like 16 plus 32 plus 1, or plus 2, right? So that's going to be like 48, like 50. So this is 50, right? And this is the standard binary form for 50. And it's also the 2's complement form, because remember the 2's complement form is no different. But if you want to find out what negative 250 is, which is right down here, first we're inverting. So we're changing the 1 to 0, 1 to 0, 0 to 1, 0 to 1, 1 to 0, 0 to 1. And then we're adding 1 right here. And if we do, I'm going to go ahead and just do the calculation right here on the side. We'd have 0, 0, 1, 1, 0, 1, and then plus 0, 0, 0, 0, 0, 1, or basically the same thing as we have right here. And we end up with 0, 1, because 1 plus 1 is 1, 0, 1, 1, 1, 0, 0, which is basically what we have right here. And this is going to end up representing negative 50. Now, one thing to keep in mind as well is that actually the way that this works is the leftmost bit. So, well, actually, we'll get into that later. I actually don't want to get into that right now. That's something for another discussion. Anyways, let's go ahead and let's look at a problem that you might see on the A-level exam. I mean, this is taken from a past A-level exam. So right here we have negative 196, and we want to see this in as a 2's complement binary integer. Now, we need to convert the value into a 12-bit 2's complement binary integer, and I'll explain why that 12 bits is important here in a second. Now, if we want to find what a negative integer is in 2's complement binary integer, the first step is always going to be to convert the positive equivalent to 196. So I want to convert 196 to a binary integer, to basically its 2's complement value, which is just the standard binary form, right? So we're going to go right down here and convert 196, and I'm just going to write out my my different powers. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. And 2 to the power of 7 is 128. If we go beyond that, we get 256, which is too much. So we're going to start right here, and we're going to put a 1 right here. Once we do that, we can subtract 128 from 196, which is just going to end up being, so that's going to be 68. So we have 68 left over that we need to count for, and 2 to the power of 6 is 64. So you can put a 1 right here, and we can subtract 64 from here, which is just going to give us 4. And so we can go ahead and put a 1 right here where we have 4, and everything else is going to be 0, 0, 0, 0, 0. So 196, both the 2's complement form of 196 and the standard binary integer form of 196 is going to end up being 1, 1, 0, 0, 0, 100. But I shouldn't have said 100 because these are binary values, but whatever. But remember, it said we want a 12-bit 2's complement binary integer. So when we do this conversion, remember this is only 8 bits right here. We need to add 4 more bits to give us 12 bits. So you have 0, 0, 0, 0. Now, here's why the 2's complement, well, the 12-bit part is important, right? So right now we have 196, and we want to find out what negative 196 is in 2's complement binary form. So to do that, first we need to invert all of the bits, meaning we need to change the zeros to ones. So we're going to have 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1. Now, if we hadn't added those extra 4 zeros for 12 bits, then we wouldn't have the ones in our 1's complement inverted form right here on the very left. And now that we've done that, we want to go ahead and add 1 to our inverted form. So we're going to do plus 1, and we're going to have 1 right there. And we're actually going to end up with 0, 1, 0, 1, 1. And then the rest is just going to be the same. So it's going to be like 1, 1, 1, 0, 0, 1, 1, 1, 1. Sorry for not making it so neat, but basically, I'll actually just write that in a different color. We're going to have 1, 1, 1, 1, 0, 0, 4 ones, and then 2 zeros. And that's going to be our answer. And again, this is in 12 bits, right? So if you go ahead and check our answer right here, yeah, we're good to go. 4 ones, 2 zeros, 4 ones, 2 zeros. And that's how that works. Now our next question is actually quite interesting. It says, give the smallest and largest 2's complement binary number that can be represented using 8 bits. Now, in order to answer this question, we need to get a better understanding of how 2's complement works. Let's look at our previous example in order to do that. We had negative 196, and this was 196, the positive 196, right? Notice that our leftmost digit right here is a 0. So if our leftmost digit is a 0, that means we're dealing with a positive number. If our rightmost digit is, or sorry, if our leftmost digit is a 1, as it is right here and right here, these are the same, then that means we have a negative number. All right, and that's something that I didn't mention earlier. Let's go back and see if that corresponds with our previous example. So right here, this is actually like, I guess this didn't exactly work out that way, right? So we started with the binary number right here, but one thing to keep in mind is that if we were really working with this in 2's complement form, like this is technically 2's complement form, but if we were getting into the nitty gritty, then we'd have a 0 right here to show that this is actually going to be positive. So right here, I would have represented this as a 0 as well. And that's maybe why some of these examples don't make as much sense as they really should. Because if I had a 0 right here, then all the way down when we got right here, I would have had a 1 right here that would have indicated that it was actually going to be negative 50. So that's a concept that you may not necessarily see, but you need to be aware of to be able to answer questions like this right here. And that's also the reason why, for example, you might have a 2's complement integer that needs to be represented as 12 bits or 10 bits or whatever is specified on the exam. So anyways, give the smallest and largest 2's complement binary number that can be represented using 8 bits. So the smallest number is going to be something that's negative, right? So it's going to start with a 1. And it's going to start with a 1, and basically if you want this to be the smallest possible value, then the rest of the digits are just going to be zeros. And that's basically going to be our answer. So we just have 1, 0, 0, 0, 0, 0, 0, 0. And this would be our 2's complement representation, 1 making it negative, and the rest of the zeros representing that value. Largest, on the other hand, we want a positive value, and then the highest possible values for the rest of the digits, which are going to be 1, 1, 1, 1, 1, 1, 1. And that's how we would represent the largest value. Now, it may not be immediately obvious, but so this is like in 2's complement form, right? And in this form, it can be a bit difficult to understand like what this actually represents, like directly converting this. If we sort of reverse engineer this, we would end up with an integer value. Here it's a bit easier because we just have 0 as our last bit, right? And so this is going to end up being 127 as an integer. If we actually went back and converted this, like if we reverse engineer this, we would get 128, which means that this is actually going to be equivalent to negative 128. I'm not going to go too much into this, but that's basically how this works. You may run into a question like this. Anyways, now that we have a good handle on those concepts, let's move on to some binary arithmetic. And this is kind of an extension of what we already did when we were converting to 2's complement. So to start with this problem right here, we're going to add 0 plus 1, which is going to be 1, 1, 0, 1. And then remember 1 plus 1 equals 1, 0 in binary. So we're going to put a 0 right here, 1 right here, and we have 1 plus 1 again, 0 right here, 1 plus here, 1 over here, 1, 1. And this is just going to be our answer right here. These are two positive integers that could be in 2's complement form. Generally, when we're doing binary arithmetic, we're going to be doing things in 2's complement form because that's just a better way to represent the various types of values we could have. Now this is represented weirdly, but if we have this, then we'll get our answer along with the work. So let's take a look at another problem right here. So this one's going to be slightly more complex, but I think you can deal with it. So we're going to have 0 plus 1, so we're going to have 1, and then 1 plus 1, so we're going to have 0, 1. And then we have 1 plus 0 plus 1 right here, so we're going to have 0, 1 again, 1 plus 1 again, so 0 and 1 again, 1 plus 0 plus 1, so we're going to have 0, and then we're going to have 1, and then we're going to have 1 plus 1 plus 1. And these are, remember, single bits, single digit binary numbers. So this is going to represent 2 to the power of 0, 2 to the power of 0, plus 2 to the power of 0, which is actually just going to give us 3. And the way we represent 3 in binary is going to be like this. So 1, 1. So we can write a 1 here, and then we can also put a 1 up, I guess carry over a 1 on top over here. So that's going to be, so we're going to end up with 1 right here, and also 1 right here. And that's just going to be our answer. So let's go double check that we got that right. So 1, 1, 1, okay, we're good to go. Now state how an overflow can occur when adding 2 binary integers. So one way to think about this is, let's assume that instead of having 0 right here, we had 1 right here, okay? So that means that we would have had 1 plus 1, which equals 1, 0. So we would basically have had to put 0 right here, and we would kind of had 1 off to the side right here. Now it kind of depends on how the question asks for our answer to be represented. But if our question was asking for an 8-bit answer, then we would actually just have to truncate or get rid of this value, and just what's here would be our answer. But anyways, I kind of went ahead there. Having a value like this as a leftmost digit is a way in how the overflow can occur. Basically, an overflow can occur when both digits are represented by a value that's greater than the number of bits that are allocated. So if we have 8 bits allocated to our answer and we have a digit that takes up 9 bits, that's how an overflow can occur. So now let's take a look at another slightly different example, but in the same format. Or rather, I would say an example in a different format, but is actually just following the same methodology and is kind of the same problem. Anyways, we have the binary contents of 2 registers right here. They're both 8-bit registers. And the question is asking us to add the contents of register 1 and register 2. So we're going to add these up, and we're just going to end up with 0, 1, because 1 plus 1 equals 1, 0. 1, 0, 1, and 1 plus 1 plus 1 is going to equal 1, 1. So 1, 1, 0, 1, 1, 1, and then 1, and then we have 0 right here. So we're going to have 0, 1, 1, 0, 1, 0, 1, 0. Now this didn't specify exactly how many bits our answer should be, but you can kind of assume that in general, if we're adding two registers, each with 2 bits, then our answer should also be 8 bits. Sorry, 2 registers each with 8 bits. Then our answer should also be 8 bits, and every overflow, or any overflow, would be cut off. But again, make sure and read the question and see exactly what it's asking for. Okay, so now we have a slightly different problem. Perform the following binary subtraction. Now, right here, we basically have a positive number. So this is a positive binary integer, and we have a negative number actually. And this, we could do some carrying over. There's like a weird way to do this, but what would be easier if we could just add this top number to a positive number below. And this is where 2's complement form is going to be used. Now this top number is already positive, and it's already in 2's complement form because any positive binary number is automatically going to be in 2's complement form as a positive number. But this is a negative value. So what we can actually do is convert this to 2's complement and then just add them together. So we basically got negative 0, we've got negative 0, 1, 1, 1, 0, 1, 0, 1. And in order to convert this to 2's complement, basically what we want to do is turn this into a positive and then go through the process of converting it to a 2's complement, a negative 2's complement value, right? So basically want to take, because basically like what we want it to get this value, we would take the positive value and go through like a certain process, right? So, okay, what we're going to do, we're going to invert all the bits. So we're going to do 1, 0, 0, 0, 1, 0, 1, 0. And then we're going to add 1. So plus 1, we're going to end up with 1, 1, 0, 1, 0, 0, 0, 1. So now what we can do is we can go ahead and we can do 1, 0, 1, 1, 0, 0, 1, 1, plus 1, 0, 0, 0, 1, 0, 1, 1. Because now this is going to be a 2's complement number, and we can just add them together as such. So 1 plus 1 is going to be 0, 1. We have 3 1s, so 1, and we're going to put a 1 right there. 1, 1, 1, 1, 0. And actually right here, we have 1 plus 1. So we're going to put 0, and then we're going to put a 1 right here. And this is going to be our answer. And let's go check. So looks like we actually got, okay, so we've got 2 zeros, a bunch of 1s, and then 1 0. And that's pretty much what the answer is. We wrote this right here in parentheses. We could also have just gotten rid of it, but I think it's just easier to write in parentheses. The question didn't explicitly ask us to do one thing or the other with the overflow, so that's basically the way it is. So basically the step for subtraction is take the bottom number, convert it to 2's complement, and then add that new 2's complement form to our top number. Now to see another example, it says the binary contents of 2 registers are as such, and we need to subtract them. Now this is tedious, but let's go ahead and do it. I'm not gonna lie, it is kind of tedious. So we're gonna take our bottom number and we're gonna do 0, 0. We're just gonna write it out actually. 1, 0, 1, 1, 0, 1, invert it, 1, 1, 0, 1, 0, 0, 1, 0. Add 1. So if we just add 1, then that's just gonna give us, I'm just gonna write it over here actually, because it's quite easy. It's just gonna be 1, 1, 0, 1, 0, 0, 1, 1. Like right here is the only, I mean, we have a 0 right there, and that's pretty much the only digit that's going to change from the bottom number that was inverted. So now that we've done that, we can go ahead and set up an add. We can add, I'll just do this in different color, 0, 0, 1, and we've got 4 1s, 0, 1, plus 1, 1, 0, 1, 0, 0, 1, 1. So if we go ahead and do that, we have 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1. Looks like we're going to end up with some overflow. 0, 1, and then we have 1, 0 right here. So it doesn't say explicitly how many bits we need, but I'm just going to go ahead and write that, and then 0, 0, 0, 1, 0, 0, 0, 0. I actually think we should just get rid of the 1 because we have 8 bits in each register, and it's kind of what we're working with. But anyways, let's just see what the answer is. Okay, so we have this right here. And yeah, it looks like they just got rid of the overflow, honestly. And that was probably the right move, I would say. Let's get rid of it. Anyways, that's it for that, and we're good to go. Now, here we have a slightly more complex question, and let's get into it. So it says hexadecimal 23 in 2's complement representation is this number. So 0, 0, 1, 0, 0, 0, 1, 1. The denary number 10 needs to be subtracted from this value. Subtract the denary number 10 from the 2's complement representation, which is actually the same thing as this above. So, okay, if we want to subtract the denary number 10, that means that it's going to be the same thing as, and we're subtracting it from a 2's complement representation. So that's going to be the same thing as adding. So adding negative 10, right? I think actually now I'm probably explaining this a bit more clearly than I did before. Like when we're subtracting, we're adding the negative 2's complement representation. That's actually, I don't know why I just didn't say that before. Anyways, okay. So that means we're going to start with 10, which actually we've kind of already done this. We're going to start with 10, and that's going to be, this is actually 8 bits right here. So we're going to represent 10, positive 10 in 8 bits. And we're going to say, so that means that 10 is going to be, so we're going to have probably 0, 1, 0, 1. That's going to be really actually all we need, right? To the power of 0, 1, 2, 3. And then we're just going to have 4 other bits because it's going to be 8 bits. And this is positive 10, but we want to turn this into negative 10 in 2's complement. So we're going to do 1, 1, 1, 1, 0, 1, 0, 1 to invert it to 1's complement. And then we're going to add 1 right here. So we're going to add all this up. So we're going to have 0, 1, 1, 1, 0, and then 4 1s, right? And okay, so we have that. And now we want to go ahead and add these two together. So add our top number. So add this. So 0, 0, 1, 0. And then 2 zeros, 1, 1, plus 1, 1, 1, 1, 0, 1, 1, 0. Let's go ahead and do that. We're going to have 1, and then we're going to have 0, 1, then 0, 1. It's going to be 1, 1. We're going to have 0, 1 right there, 0, 1, and then that's just going to give us 1, 0. So presumably we're going to kind of get rid of this. We're just going to have 0, 0, 0, 1, and then 1, 0, 0, 1. Let's go see if we're right. And are we right? Yeah, we're good to go. Again, there's overflow, but we didn't really end up going through that. But this was 3 points because we need to go through this whole conversion process. And then after that, we need to do the addition and then get the right answer. Okay, so next question, logical shifts. I'm not going to spend too much time on this because I think it's like pretty straightforward, honestly. But right here, we want to do a 3-place right logical shift on the binary number. That basically means we're going to move all the numbers 3 places to the right. So the right is on this side, so we're going to do that. And basically, it means just getting rid of these 3 numbers. So we end up with 1, 1, 0, 0, 1. But we're getting rid of those numbers, but we still need to have 8 bits. So we're going to have 0, 0, 0 right here. That's pretty much it. Like if we had like a 2-place left shift, right? We just move everything to the left. So like we would get rid of these 2. We just have 0, 0, 1, 1, 0, 0, 0, 0. So that's pretty much how that works. So let's actually just check the answer and just make sure that I'm not an idiot. And okay, I think we're good to go. That's basically how logical shifts work. You will move either to the right or to the left, and whatever you get rid of, you need to add a corresponding number of zeros to the other side. Here's some examples. So right here, we have a left logical shift, and basically we got rid of this right here, and we moved everything to the left, and we added a 0 on this side for that remaining spot. Right logical shift, again, we ended up getting rid of this right here, and we moved everything to the right, and we just added a 0 to this side right here. This actually looks a little bit different than the way I explained it, but the result is the same. This is something that's covered more in depth in paper 3. Okay, so as we said before, binary is the language of computers. And so now we're going to start taking a look at different ways that we can use binary to represent, for example, now text, and later on images, videos, and audio. So let's get started here with text. Now, one way we can use binary to represent text is through a format called American Standard Code for Information Interchange, or just ASCII. Now, what this means is that we have about 128 characters that we can represent, or this format basically allows us to represent 128 characters, including things like uppercase and lowercase digits, as well as symbols like the pound sign or slashes or whatever. Now, the key behind this is that we could use 7 or 8 bits to represent each character. Each character is represented by a unique binary code. So to kind of summarize, ASCII is a format that allows us to represent 120 different characters as binary code. And this is often something that's built into the operating system or software that is being used. The problem with this, however, is that it's only limited to the Latin alphabet. If you look at this chart right here, which again is basically all of the ASCII possible characters with the numbers that would represent them in binary, we don't really have a way to represent other languages, which is a problem given that computers are kind of a global thing. Hence, we developed Unicode. Now, Unicode supports 150 different scripts, including Latin, Greek, Cyrillic, which is used for some Slavic languages, Chinese, Arabic, and Devanagari, which is used for Hindi. And actually, I think it's used for some other languages on the Indian subcontinent. I don't know if it's just Hindi. Anyways, now rather than just being able to represent 128 characters, using 7 to 8 bits for each character, we can use anywhere from 8 to 32 bits to represent characters. And partly because we can use something like 32 bits and 4 bits equals 1 hex value. Right here, you see the hex representations for different Chinese characters. Now, if we compare both of them, Unicode is made up of up to 32 bits, and ASCII is made up of 7 or 8 bits, which is the reason why we can represent a wider range of characters using Unicode, particularly for different languages. However, they're both the same in the fact that their ultimate goal is to represent characters using a unique code. Unicode just provides us with a much wider range of characters for different languages that we could use. So now let's take a look at a problem based on what we just learned about. State the number of characters that can be represented by the ASCII character set and the extended ASCII character set. So ASCII is just going to be, we can represent 128 characters. That's standard ASCII. Now we haven't talked about extended ASCII, but basically it gives us an extra bit and means we can represent 256 characters. That's really the only difference between the two. Now, next, explain how a word such as house is represented by the ASCII character set. So basically we need to go through just the process of how this is represented. And basically what happens is if we want to represent house, then we need to convert each letter to its matching binary equivalent based on ASCII. So based on ASCII, we're going to have a binary value that represents each of these letters. So H in uppercase, O in uppercase, etc. And then we're going to take those binary values and then put them in the same order as the letters in the word. So we'd have the binary value for H followed by O, U, S, and then E. Now if we go to the mark scheme, basically what that looks like is each character has its own unique code. Each character in the word is replaced by its code, and the codes in the word, or the codes are stored in the order in the word. Now our next question looks at Unicode. So right here it says Unicode is a different character set, and like obviously we know that, but remember one thing to keep in mind is that Unicode uses hex. So the Unicode value for the character 1 is denary value 49. Write the hexadecimal value for the Unicode character 1. So basically what we want to do is we want to take this and convert it to hex. So like for me, the easiest way actually to do this is to convert to binary first. So I'm going to go from 49 to binary. So let's see, 2 to the power of 5 is 32. So that's going to be a 1 right there. So 49 minus 32 is going to be equal to, what is that, 17. Then 2 to the power of 4 is going to be 16, which means I'm going to put a 1 right there. So I'm going to have 1, 1, and then 0, 0, 0, 1. And that's going to be my binary value for 49. So 25 plus 16, sorry, no, 32 plus 16 is 48, plus 1 is going to be 49. But what I want to do is turn this into hexadecimal, so I want 4 bits. So it's going to look like that. And this is just going to be 1 in hexadecimal, right? So this 4-bit value is just going to be 1. And this 4-bit value, that's just going to be 3. So that means the hexadecimal value is going to be 3. So 31. So, all right, we have 49. So we have 49, and that's going to be represented by 31 in hexadecimal. And that represents the character 1. Now, next is write the denary value for the Unicode character 5. And if the denary value of 1 is going to be 49, then that means we're going to have to move, that means that 2 should probably be 50. Then 3 should be 51, 4 should be 52, and 5 should be 53. Let's go see if that's true. Yeah, that is more or less right. I mean, 5 is really just 4 places over from 1, and everything is going to be in sequential order. So that's why if 49 represents 1, then 53 has to represent 5. Anyways, that brings us to the end of our first section. Next, we're going to look at graphics and how images can be represented using binary. So the first sort of concept that we need to understand when understanding how binary is used to display images is the idea that, first of all, what we see on a screen, so our entire screen is divided into pixels. And images as well, when they're displayed on a screen, are divided into pixels. So for example, this might be a picture right here. And this picture is essentially a grid of pixels. Each pixel is a small square that makes up that particular image. Now, if we have a collection of squares making up an image, each square being called a pixel, then each one of those squares is going to have its own color and intensity. Now here, this is an extremely simple image. It's only black and white, but in this case, 0 might represent white and 1 might represent black. So in order to represent this image, we would actually have something that looks like this. So we'd have something that looks like this right here. And this could be stored in a computer in the form of a 2D array or some other data structure. But that would be representing this image right here. As you can see right here, a particular pixel with the bit 1, with the value 1, is going to be black right over here. Now, this is the idea behind bitmap images, the idea that a map of bits or a grid of bits is being used to represent an image. And this is really simplistic, but if we have an image that's made up of thousands of pixels, then we could have something that is much more sophisticated, that's an actual image that you might see today, like on your screen. Now, bitmap images are basically the image formats such as JPEG, PNG, GIF, or BMP that you've probably seen before if you've done any sort of work with media. And obviously these formats are widely used in digital photography, web graphics, and just in your usual desktop application. But this idea of an image, of your screen and of an image being represented by a grid of pixels, and each pixel corresponding to a single bit, a 1 or a 0, or a certain number of bits, is fundamental. Now, we looked at an example where an image is a grid of bits, of individual bits, of 1 bit. But here we have an image that is represented, it is represented by a grid of pixels, but each pixel is going to be represented by 3 bits. So in this case, instead of just having black and white, with black representing, was it 1 and 0 representing, or white representing 0, or 0 representing white, we have the option for a variety of images. We have 3 possible bits for each image, and so 2 to the power 3 is going to be 8. So that means that each pixel, sorry, I didn't mean to say image, but we have 3 possible bits for each pixel, and that means that we have 2 to the power of 3, or 8 possible colors for each pixel, which is going to give us a lot more possibilities for this image right here and just representing images in general. So the more pixels we have, the more colors that we can represent, and the more different intensities that we can represent for each individual pixel, or each individual square, right? Also, one term that I do want to go over, I mean, this was entitled color depth, but the number of bits that's used to represent each pixel is going to be color depth. And that brings us to my next slide, which is going to give us some terminology that allows us to deal with the concept of bitmap terminology and just representing images in general. First is pixel. So pixel is the smallest unit of a bit-matched image, representing a single point of color or a single square. Now, as I said before, screens are made up of a set number of pixels, like for example, 1920 by 1080, with 1920 being the width of a screen and the height being 1080. And this basically means that we have 1920 pixels as the width, 1080 pixels as the height for a screen. And so that basically represents the size of images that we can display. And each pixel will have a certain number of bits attached to it to display an image. Anyways, we have pixels, we have file headers. Now file headers are metadata, so they're basically additional information that you can access that are attached to an image file, and they contain information such as dimensions, color depth, and compression type, not comprehension, compression type. And we'll see more about what compression means, and we'll talk about image dimensions here in a second. Now, with image dimensions, we're talking about, again, this. So here I give the example of a monitor being able to display pixels, a certain amount of pixels. So basically, if we have a monitor that has a width of 1920 and a height of 1080, then 1920 times 1080 would be the number of pixels that can be displayed, and that can be used to display any other images on a screen. And so basically our image dimensions would be a width by height in terms of pixels, and image resolution would be the number of pixels in an image. So for example, if we did have an image that was like this, or if you had an image that was 800 pixels wide by 600 pixels in height, 800 times 600 would end up being our image resolution. Like, I don't know what that is. I think it's like 480,000 pixels. But so our image resolution is going to be the number of pixels. Our image dimensions are going to be the width and the height. So this would be like our width and height, and that would be like an image dimension, and the number of pixels would be the image resolution. Now, this is getting into a concept that I talked about a lot earlier, and that's screen resolution. So we have image resolution, which is going to be the number of pixels in an image, and we have screen resolution, which is going to be the number of pixels in the screen. And here I gave the example of 1920 by 1080 being like the dimensions of a screen. So that means if we multiply these, that would be our screen resolution. Now fundamentally, like, we're using the same concepts for both image and screen resolution. Image resolution is going to be how many pixels are in an image, and screen resolution are going to be how many pixels can be displayed on a screen. And finally, we have bit depth. And bit depth is just the number of bits used to represent each pixel. So for example, here we had a bit depth of 3 because we could use 3 bits to represent the colors in each pixel. And here we had a bit depth of 1. So now that we know that information, let's go ahead and let's solve some A-level problems using what we know. So it says right here, a bitmap image has a resolution of 2048 pixels by 1024 pixels. The image has a bit depth of 10 bits per pixel. Estimate the file size of the image of the bitmap image in megabytes. Now remember, megabytes are going to be, so 1 megabyte would be 1024 kilobytes, and each kilobyte would be 1024 bytes. So first of all, let's go ahead and let's try to figure out how many bits we have as a whole. So the image has a bit depth of 10 bits per pixel, right? And we know this is the resolution of the image. Or it's the image resolution. So that means that the number of bits we have is going to be 1048 times 1024 times 10. So that's basically going to be the number of bits that we have. Now, what I'd want to do to get the number of bytes is I would divide this by 8. Okay, so that would give us a number of bytes. Now, if we have the number of bytes, we want to figure out how many megabytes that is. So what we'd have to do is we'd have to divide that by 1020. So this is going to give us, this top portion is going to give us a number of bytes. So we're going to divide that by 1024. We'd have to divide by 1024 to get kilobytes, times 1024 to get megabytes. Because remember, 1024 bytes, so megabytes are going to be 1024 times 1024, because 1024 times the number, or 1024 bytes is going to be kilobytes. So if we multiply that by 1024, then we get a megabyte. So 1024 bytes is 1 kilobyte. We multiply that by 1024, then we'd get 1 megabyte. So I actually don't know what this is, but let's go and check the mark scheme. It looks like I actually did the math correctly. It looks a little bit different here, but the result will be the same. I don't know what the number is, but apparently that was good enough. So, I mean, also basically like my math, like I divided by 8 right here, but that's going to be like the same thing as multiplying by 1/8. So we'd have 2048 times 1024 times 10 times 1/8 times 1/1024 times 1024, which is why the mark scheme shows an answer. It looks like this, but again, I think mine would be good. Oh, right here it does say it's around 2.5 megabytes. Anyways, let's move on. State what is meant by bit depth of a bitmap image and explain how changing the bit depth affects the image. So bit depth, remember, is the number of bits used to represent each pixel, and the higher the bit depth, the more colors we could display in an image, and the more detail with which we could display the image. We can also change things like the intensity of the colors. So basically we can represent the image, it affects how clearly, and yeah, basically with the amount of detail that we can show an image. This one's about compression right here. Explain why bitmap image is often compressed before it is attached to an email. Now we're going to talk about compression later, but the most likely reason is because if we compress it, then it'll just take up less space and it takes less time to email. The email itself is smaller. Now another question, one of the photographs has a bit depth of 8 bytes and an image resolution of 1500 pixels by 3000 pixels. Calculate the file size of the photograph in megabytes. So, okay, we have a bit depth of 8 bytes. So that means that the number of bytes is going to be 1500. So again, 8 bytes per bit means that we have 8 bytes for every single pixel. So 1500 times 3000 times 8, right? That's going to give us a number of bytes. And 1 megabyte is going to be 1000 times 1000 bytes, because one kilobyte is 1000 bytes, and 1 megabyte is 1000 kilobytes, right? So we're gonna have 1500 times 3000 divided by 1000 times 1000. And I'm actually not sure what that is, but if you go here, it looks like my math is right, and that ends up being about 36 megabytes. Also, just to go back, if it wasn't actually clear when we solved this problem, the reason I divided by 8 was because we had 10 bits per pixel, and we had to divide by 8 because it's 8 bits to 1 byte, right? So right here, we would get the number of bits and then divide by 8 to get the number of bytes, and then divide that by 1024 times 1024 to get the number of megabytes. And again, 1 kilobyte equals 1024 bytes, and 10 and 1, I don't even know how to write this, 1 megabyte equals 1024 kilobytes. Hence the reason for our calculation right here. Just wanted to clarify that. Anyways, a few more questions. Describe the impact of increasing the image resolution on the quality of a bitmap on a bitmap graphic. So increasing the image resolution means adding more pixels. And this could actually mean two things. This could mean that the image is going to be larger, or that just like the image is going to be much more detailed, because we'd have more pixels. And if we're not increasing the size of the image, we have more pixels. That means that we're going to be able to display more detail and be less pixelated. Like we just have more pixels that allow us to display more colors and more different colors, more different features in a fixed area, so like in a given area. And I think probably the mark scheme expresses that better. It says more pixels can be stored, and so the image is sharper and less pixelated. Now next we have another calculation. So calculate the file size of a bitmap image using the following information. Image resolution of 2048 by 1024 pixels, and bit depth of 16 bits. Give your answer in kilobytes. Okay, so first we want to get the number of bits, which is 2048 times 1024 times 16 bits divided by 8, right? That's the number of, well, okay, so this part right here is going to be the number of bits. We divide by 8 to get the number of bytes, because 8 bits equals 1 byte. So this whole expression right here is going to give us the number of bytes. And we want to give our answer in kilobytes. And we know it's 1 byte to 1,000 bytes to 1 kilobyte. So that means in order to get the number of kilobytes, we need to divide by 1,000 bytes, and that would give us our answer. Now again, I don't have a calculator, but it turns out that that's like 4,096. As you can see, the expression I used is correct. 4,096. Now let's take a look at some factors that affect the image quality of bitmap images. There are a bunch of terms here that we've gone over before. So the first two I want to look at are pixels and image resolution. So basically, if we have an image, the more pixels we have in a given area, the more detail that we can represent, the clearer the image is going to be. Let's just take this for an example, right? So if I draw this right here and I create a grid of 9 squares, I have 9 pixels in this image. However, so we could use these 9 pixels to display some kind of image, but if I then multiply the number of pixels by 3, and then probably by 9, then I can display a much more detailed image than I could before with just 9 pixels, because I've increased the image resolution. Generally, the more pixels per a given area, or in this case per inch, the more detailed an image and the better the quality is going to be. And overall, the more pixels in an image, again, the higher detail we're going to be able to display. Now, regardless of the image resolution, the resolution of an image, if we don't have the screen resolution that at least matches or exceeds that, it doesn't really matter. So in order to be able to display images of a high image resolution with a lot of pixels per inch, we also need a screen to have a resolution with that many or more pixels per inch. Now, this allows for the display of more sharper and more detailed images, similar to what we talked about before. Beyond just that, in order to have a higher image quality, we also need to have a higher bit depth. And the bit depth is the number of bits that decide the image that's going to be represented in each pixel, or in each square in our little grid. The more bits we have, the more range of colors we can represent. Some common bit depths are 8 bits, 16 bits, etc. So if we have 16 bits, we have a higher choice of colors that we can display than if we just have 8 bits per pixel. Therefore, the higher the bit depth, the more realistic the image is going to be, and the overall better quality the image is going to be. When we have a low bit depth, then we get something like this. This is called banding, and we don't have sufficient bit depth for the colors that would allow us to transition between different bands, so different areas of different color in our image, and hence we get something called banding. If we have not only a low bit depth, but we have a low image resolution, things can also look pixelated, and that's where we have like kind of a chunky, we see like kind of chunky squares in our image. We don't really see that here, but that's a possibility. However, if we do have sufficient bit depth and we do have a good image resolution, we'll see something that looks more like this. Now, beyond just looking at image quality, file size is also important, particularly when we want to do things like email images to other people or upload them to a website. Now, as a rule, the higher image resolution we have, the higher the file size is going to be. Because remember, each pixel is going to have a bit depth, maybe like 8 bits. And the more pixels we have, the more pixels we have, the more of these 8-bit units that we have, right? So for example, if we have 60 pixels, then to get the number of bits, we just do 60 times 8. And that would give us a number of bits, or really this would just be 60 bytes, right? Because 1 byte is 8 bits. However, if we had 120 pixels in an image, or if we had 120 pixels in the same area, so let's say this is 60 pixels per square inch. If you have 120 pixels, then in that same area, we would have the equivalent amount of data of now 120 bytes, right? So we'd have double the amount of data for that particular square inch, increasing the file size by 2. Now, even if we have a lower image resolution, if we do have a higher screen resolution, then this is actually going to end up increasing our file size because images are going to be created on that computer when we open it up at a higher resolution for better display quality. So if we wanted to lower the file size, we'd also need to have we'd have to have a lower number of pixels, but then we would also need to we'd ultimately need to display that on a screen that has lower quality, or that displays images at a lower screen resolution. Now finally, the third factor affecting bitmap file size is going to be the bit depth, right? So if you have 60 pixels per inch and we have 8 bits per pixel, then that's going to give us 60 bytes. But if you have 16 bits per pixel, that's going to be 120 bytes in that same square inch. So the more bits that we use to represent each pixel, the more overall data we're going to need to store in order to represent an image, and the higher our bitmap file size is going to be. Now to kind of put this all together, let's look at an A-level question. So here it says the following bitmap image has a resolution of 4096 by 4096 pixels and a color depth of 24 bits. Remember, a color depth is another word for the bit depth. Now here it says the image is displayed on a monitor that has a screen resolution of 1922 by 1080 pixels. So if we change the color depth of the image file to 16 bits per pixel, we're actually going from 24 bits to a lower bit depth, or a lower color depth. That means that each pixel will be represented by a fewer number of bits, and therefore we're going to decrease that file size. Now, if we change the screen resolution to 1366 by 768 pixels, we're basically making the screen resolution lower. So we're not really going to see a change in file size, because if we reduce the screen resolution, which means the detail with which things are displayed on the screen, that's not going to cause us to decrease the file size. That just means there's going to be no change in file size. Next, change the color of the rectangle from black to red. Simply changing the color is not going to make a change to the file size. We're still going to need to, I guess by a rectangle, I think a rectangle is maybe a rectangle in the image, but we're still going to be using the same number of bits to represent each pixel, regardless of what the color is. So there's going to be no change to file size as well. What is important to understand or remember though, is if we did increase the file size or the screen resolution, so if our monitor had a higher screen resolution, then we may end up increasing the file size. But that wasn't the case here, So for the second one, we're good to go. And the next concept we're going to get into is called vector graphics. So with vector graphics, we're no longer creating images with just pixels, but we are actually using mathematical formulas to define geometric shapes that will then go ahead and make up our image. These are resolution independent, meaning no matter how big or small we make them, they're going to look the same without losing quality. Because again, we're not using individual pixels to necessarily represent them or represent each color or each shape or any of the forms, any of the shapes or any of the different, let's say lines that make up the image. We're really just using a mathematical formula. So when we want to create this image, we're going to use the mathematical formula, and then we're going to end up generating an image at whatever the image quality is, or the image resolution is, of the screen that we are displaying this on. So I guess rather at the screen resolution of the screen that we're displaying this on. So what's important here is, let's say we have an image like this. If we're using a bitmapped image, then basically when we store this, we're going to be storing the number of bits. We're going to be storing number of bits for each individual color, right? And then when we go to open that up on a computer, we're just going to go ahead and display the ones and zeros for each one of these pixels to be able to display the image. The vector graphic instead, we're going to have some formulas, and those formulas are going to be used to generate an image at whatever image resolution we want it to be at. So it doesn't have to be fixed. It doesn't have to be at whatever image resolution we specified here, but it can be pretty much anything we want. And this is used for logos, illustrations, and graphic designs because a lot of times we'll need to resize logos depending on whether we're putting them on a website, on paper, whatever. Now, remember for Bitmap Images, we had some formats like JPEG, PNG, etc. But for vector graphics, we're going to have file formats like SVG, EPS, and AI. And if you've ever worked with Adobe Illustrator, then you've seen these image formats before. So again, just to kind of summarize, we're not displaying, and I guess we're not representing images based on each individual pixel and the color that corresponds to it, but rather we're displaying it based on mathematical formulas, which are then used to create an image at whatever resolution we want the image to be at. So we do have some terminology we need to learn in order to talk about vector graphics, similar to how we had to learn some technology to talk about bitmap images. So basically, vector graphics have a drawing list, and it specifies each object and its properties that are going to make up the image that we want to be able to represent. And this list is going to allow us to ultimately create our image that is both scalable and editable without losing any quality at all. Now, the first aspect of a vector graphic is going to be a drawing object. And this is going to be an individual object located in the image that's defined mathematically. A drawing list is going to be a collection of drawing objects that make up our image. So for example, if you had a house, let's say this is our image right here and we have a house, then for this triangle right here, that's going to be a drawing object, and we'd have some mathematical formula to represent that, or some sort of equation to represent that. Then we'd have the square right here, and the mathematical expression. I guess I'm using mathematical expression, formula, whatever, but okay, let's just call it a formula. Let's say it's some mathematical representation. One formula is going to be used to represent the square, the other formula is going to be used to represent our triangle, and both of those formulas are going to be in our drawing list. Now, we can say that we have one object which is a triangle and one which is a square. And for that triangle, we're going to have other pieces of data that tell us what the color is, what the thickness of the line that makes up each of those shapes is, and with what pattern we're going to fill that up. So we have a drawing object, which is the individual objects in our image. We have the list, which is just a list of the formulas that represent each one of those objects. And then for each drawing object, we have a property that gives us some parameters, some characteristics of each of those objects so we know how to display them. So if you look at an A-level question right here, we have a drawing list, a drawing object and a property, and we need to match them to their correct definition. So a component created using a formula is going to be our drawing object. A property defines one characteristic of a component, so that could be like the color, the line thickness, whatever. And the drawing list is going to be the data required to create all components in the graphic. So they're using the term component for basically the shape that we talked about right here, like a square or a triangle. They use the term component for that. Now I wanted to finish this off by comparing both bitmap images and vector graphics. So to kind of tie everything together, or really to summarize, we represent bitmap images by representing a grid of individual pixels. So we're using individual pixels to represent the image as a whole, versus with vector images, we are creating that image using mathematical formulas to define the different shapes that are in that particular image. Now with bitmap images, if we make an image in a certain resolution and we try to increase the size, then we're gonna have pixelation, and because we never had enough detail for a larger image in that bitmap image, so because we don't have enough pixels to represent that image at a greater size, then it's just going to look terrible. However, with vector images, because we're not using pixels to represent an image, we're using mathematical formulas, we can resize them as much as we want, and we're not going to have any problem. So fundamentally, bitmap images are tied to their image resolution, to the number of pixels per given area, like a square inch. And so if we try to make it bigger, then we're just not going to have enough pixels to represent an image at the same quality as it was before. There are a fixed number of pixels for that given area. Versus vector images, we can expand the number of images that are used to represent a given area to whatever extent we want, because we have a mathematical formula, not just fixed pixels, pixels that have a color that isn't going to change. Now, bitmap images are used for handling complex detail and texture as well, because particularly if we want to increase the quality, we can just add more pixels. But if we want detail, vector images are not as good, because it's much more difficult to represent an image with great detail using a mathematical formula. Because the more detail you have, the more we want to be able to precisely account for each pixel. And the mathematical formula is more of like a rule, it's more of like a summary of how an image would look, and therefore we're just not going to have as much detail. And because of the characteristics we just talked about, bitmap images tend to be better for things like photographs, and vector images tend to be better for things like logos, illustrations, graphic designs, and basically something where we care more about what it represents, what the image represents, and not the individual details in that image. So also think about like a diagram or something like that. That's what a vector image is going to be better for. Now that wraps up our section on representing images. Let's move on to sound. Now we just talked about using bits to represent different pieces of an image. Similarly, we're going to use sound. We're going to use bits to represent different pieces of a clip of audio or some sound over time. Now here's how this is going to work. First, we're going to do something called analog to digital conversion. So analog is just the sound in the air. It's continuous, it's not discrete. And we want to convert that to some number of bits. So someone's singing, we want to convert that to digits, to binary. Now, if someone's singing, we're going to have a continuous sound wave that's going to go into a microphone. And in that microphone, we're going to do our analog to digital conversion. And basically what we're going to do is we're going to record the sound at discrete intervals. So for example, if someone's singing for about, let's say 5 seconds, right? Then at different points when they're singing, so right here, 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 and so forth, we're going to record the note of sound at that particular point in time. Or yeah, basically like what sound is heard at that particular point in time, so that we can put all of those different sounds we heard at those points to approximate what the sound of that person was like singing, or an audio clip of that person singing. So that's basically how it works, and the number of intervals we have for a given amount of time. So the number of times we are sampling the sound through a microphone or through a recording device is our sample rate. So let's say that this sound clip is for 1 second, right? And we're going to sample, let's see, 1, 2, 3, 4. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that means we're taking 16 samples per second. So that means that our sample rate would be like 16 hertz per second. So that means that we would be, in order to record audio for 1 second, we would be we'd be recording that audio, or taking note, or checking what note is being played or is being sung 16 times in that 1 second. So 16 times in 1 second in order to record someone singing is really just not very much. It's not very high quality. Some other I would say some more common sample rates for like CD quality or professional audio would be like 44.1 kilohertz per second. So for example, that would be 44.1 times 1000 times per second as taking a sample of what note of audio we're hearing. Or if you have 48 kilohertz, that means 48 times 1000 samples per second of our audio that is being input. And these are generally what we'll be working with today when we're talking about audio quality. Now, I talked about notes because notes are kind of like a way we describe what's being heard. But what a note really is in physical terms is going to be the amplitude of sound. So each one of our intervals, we're really recording the amplitude of sound at that particular interval, right? And that amplitude is going to tell us basically what it sounds like. So if we have 48 kilohertz, that means that in 1 second we're recording the amplitude of the sound that's being input into a recording device 48,000 times. And each time we record the amplitude, so each one of those 48,000 times, we're going to store that amplitude in bits. So for example, right here, we have a sample rate of 16 hertz, right? So all that means is that each one of these 16 hertz is going to be, so the amplitude of each one of these 16 intervals is going to be represented by a certain number of bits. So it could be 16 bits or 24 bits. And similar to images where more bits per pixel give us more detail, more bits per interval gives us a more accurate representation of sound. So in order to get higher sound quality, we're going to have a combination of having a higher sample rate, so checking more often, and then a higher bit depth, so recording the amplitude in more detail for each interval. And remember, bits are basically representing ones and zeros. So that means we're going to end up with a file that consists of ones and zeros for the amplitude at each interval. And this data is going to be encoded into a specific digital audio format that we'll specify, which could be WAV, MP3, or FLAC, among many others. WAV being uncompressed, MP3 being compressed with some loss or reduction in quality, and FLAC meaning compression without loss. Now, we're storing this audio as bits according to the given format that we've chosen. If you want to later play back this audio, then we're basically going through this whole process in reverse. We are basically looking at the bits for each sample we've taken. So each of, for example, the 48,000 samples you've taken per second, and we're going to turn those into an amplitude. We're going to turn those into an amplitude of sound, or basically an analog signal that's going to be played through our speakers. And we're going to do that using a device called a digital to analog converter. Both the analog to digital converter and digital to analog converter are going to be electrical devices that allow us to perform their respective function. But basically right here, when we play it back, we're looking at each one of those intervals, each one of those samples, the number of bits used to represent that sample, and based on that, we're producing sound at the respective amplitude. And collectively together, this is going to give us a song or whatever that person sang in this 1 second that we were talking about right here. Now, there was a lot that went on in that explanation, but if you want to summarize this according to the A level and what the A level says about this process, we can say first, the amplitude is recorded a set number of times a second, and that's like the note of the sound, right? It's like A sharp or whatever it is. Next, each amplitude is given a corresponding binary number, and that's going to be our 16-bit or 24-bit number. And finally, the binary number is saved in sequence. So if we go back to our explanation right here, and for example, we have 16 samples per second, we're going to store the first sample, then the second sample, then the third sample, all in sequence. And together, it's going to allow us to be able to make up the sound and actually allow us to output the sound that was initially recorded. Now, before we move on, I do want to go over the terminology that we discussed earlier, just so that there's no confusion when we tackle more complex concepts. Now the first is sampling, and this is the process of converting an analog signal, like something we're hearing in nature, so just sound out in the open, into discrete digital values. And this is the process by which we're taking samples at a given point, and we're recording the amplitude there. And I talked about notes and I talked about sound, but amplitude is really just going to be the height of that particular sound wave. Remember, sound is made up of waves, so we're recording the particular amplitude or height of that wave at a given point in time. That's sampling, just basically getting the amplitude in from our recording device and turning it into a binary value, and then putting those binary values together in sequence at regular intervals. So the recording process is happening at regular intervals. Now the sampling rate is the number of samples taken per second, measured in hertz. So if we have a sampling rate of 16 hertz, that means we're taking 16 samples of the sound amplitude per second. If we have like 16 kilohertz, that means we're taking 16,000 samples of the sound per second, which is going to give us a lot more detail. That brings us to sampling resolution. Sampling resolution is the number of bits we use to record the amplitude of sound at each given sample. So if we have 16 hertz, then for each one of those samples per second, we might have like 8 bits. That means that to record 1 second of sound, we'd have 8 times 16, and that equals like 128 bits, which means we'd be using 128 bits to record a second of sound. So each one of those samples we're taking, the number of bits by which we're storing the amplitude at that particular sample is going to be our bit depth or sampling resolution. And we're using this term bit depth, which was a term that we saw before when we were talking about images, to represent the number of bits used to represent each pixel. Except instead of representing a color, we're representing an amplitude of sound. Now we talked about analog and digital data. And analog data is just sound signals in like real life, like out in the open. And these are really variations in air pressure. And we're basically making sense of them or recording them in terms of amplitude of sound waves. I mean, continuous sound signals consist of sound waves. And this wave is going to be that it's representing that variation in air pressure. Again, I'm not a physics major, so like I don't know exactly like how to explain this in the best possible way, but hopefully this makes sense to you. Now, one thing to keep in mind is analog signals are smooth and continuous. So it's just a continuous stream of data versus the digital representation is going to be discrete. It's going to be discrete according to the sample rate. So that means we're going to have, this is going to be our digital sound wave, where each one of these little points right here, each one of these little steps is going to be our representation of sound. Where in analog, it was all one smooth curve, right? And so our digital representation is going to be discrete, and it's going to be a numerical representation of the sound. And essentially, it's a series of binary numbers that can be reproduced later on to output that sound through a speaker. Now, similar to images, there are some factors that can affect file size and accuracy. So the higher the sampling rate, so the more samples we're taking per second, and the more bits we're using to represent that sample, the higher our file size is going to be, simply because we have more bits for a given amount of time. However, the more times we record the sound, or we take a sample per second, the higher the bit depth per second, the more accurate our representation is going to be. So if we want sound to sound more like it does in real life, we need to take more samples per second, and each one of those samples needs to have a higher number of bits in order for us to more accurately represent the amplitude of sound at that particular point in time, and then more accurately represent some audio or some sound over a given point in time. So basically, both sample rate and sample resolution can be used to represent sound more accurately. The higher they are, the better our sound is. The lower they are, the lower quality our sound is going to be. Now, as usual, we're going to look at a few A-level questions in order to tie all the concepts together that we've gone over. So this question is explain the impact of changing the sampling resolution on the accuracy of sound recording. So we're talking about sampling resolution. We're basically talking about the number of bits per every sample. So if we increase the sampling resolution, then our sound recording is going to be more accurate because we're more precisely representing the amplitude at a given sample. If we decrease the sampling resolution, then our accuracy should go down. But let's see what the mark scheme says. So it says right here, 1 mark for each bullet point, and this is 3 points. Number of bits used for each. So if we increase the sample of resolution, the number of bits used is increased. There'll be more values able to represent each sample. So we have more bits, we can more precisely represent the amplitude. You also need to mention the fact that each binary amplitude is closer to the analog. So our binary representation is going to be closer to what we hear in real life. So basically what this question is doing is, well, in this question we need to talk about what happens when we increase and decrease and more or less express how we actually engage in sampling in the context of sampling resolution. So really, to get the maximum number of points, you want the impact of increasing, of decreasing, and then talking about how basically if we hit the more bits we use, the closer the digital sound wave is to the original analog sound wave. Next, we saw a question like this about images. A digital audio message needs to be recorded, and we need to look at how these actions will affect the accuracy of the recorded audio. So if we change the sampling rate from 4,000 kilohertz to 60 kilohertz, we're taking more samples per second of the sound, so our accuracy should actually increase. If we change the duration of the recording, it's not really going to make a difference. It's just going to be a longer recording. It's not going to affect accuracy. If we change the sampling resolution from 24 bits to 16 bits, we're using fewer binary numbers, fewer bits to represent each sample, which means that our audio accuracy should decrease because we're not as precisely representing the amplitude at a given sample. Now next, we have a calculation question here. The audio message is recorded with a sampling rate of 50 kilohertz and a sampling resolution of 16 bits. The recording is 20 minutes in length. Calculate the file size of the recording. So what I'm actually going to do here, I'm going to do the calculation out, and then we'll check the mark scheme to see the megabytes. If my calculation is correct according to the mark scheme, then that should be the number of megabytes anyways. But we have 50 kilohertz, right? So that means that we're sampling the audio 50,000 times per second. So, and for each one of those samples, we have 16 bits, right? So we're going to do 50 times 1,000 for each second, right? And so that's 50,000 samples per second times 16 for each one of those samples. So this is going to give us the number of samples for 1 second. But we have 60 seconds in 1 minute. So we're going to multiply that by 60 to give us the number of bits used per 1 minute. And then we have 60 minutes in 1 hour. So actually, we don't really need to go that far. So we went from, so just to kind of go over this again, we've got 50 times 1,000 samples per second, right? Times 16 bits per sample. So this is going to be the amount of data for 1 second, okay? And for 1 minute, we want to multiply that by 60. So this is going to be the amount of data for 1 minute. We have 20 minutes. So we want to multiply that by 20. That's going to be our total number of data, and that's going to be in bits, right? Because we're still working out of this using the 16 bits figure. So that's going to be right now, this is bits. So what I want to do is I actually just want to go ahead and erase this right here. And we want to convert these bits to megabytes. So in order to get the number of bytes, we're going to divide by 8. And then we're going to divide by 1,000, because that's going to give us bits and then kilobytes. And then we're going to divide by 1,000 again for megabytes. That should give us a number of megabytes. Let's go check the mark scheme. And yeah, I mean, that's pretty much what it is. So we have this calculation, 50 times 20 times 60. So we have 15 times 16.
then 15 times, and then multiply by 60, and then by 20 for the number of minutes. That's going to give us a certain number of bits, and that's going to give us a certain number of bytes, kilobytes, and then 120 megabytes. Now, one thing they did right here is they multiplied by 2 bytes, but when we divided by 8, that basically gave us the same thing. So our answer is going to be 120 megabytes. So we've just finished up with audio, and we've also talked about how we can represent images digitally, as well as other types of information. Let's take a look at compression, which is important for storing and transferring this data. So why do we need compression? Efficient data storage. Remember, what compression is it basically allows us to take some file and make it smaller using either lossy or lossless compression. So we want to make these images smaller so that we can more efficiently store that information. It basically will take up less space. And if we don't want to sacrifice quality, we can use lossless compression, which uses an algorithm to compress our data, rather than lossy compression, which just gets rid of some information in order to make the file size smaller. You may want to use compression for faster data transmission. Maybe if you want to send that data through an email, send an image, or send it an audio file, you might want to compress it so we can more quickly send that image. And the person on the other side can more quickly download it. And that may not just be an image, that could be any type of file. We may have a large amount of data to back up an archive, and we might want to use compression in order to minimize the amount of data we're adding to that archive. And finally, we might want to use compression for optimized web performance, particularly with things like images. If we have a smaller file size for an image, the less amount of time it's going to take for that image to load on a website, and that's going to enhance user experience. Now, as I said, we have two types of compression. We have lossy and lossless compression. With lossy compression, we're basically just removing data to make the file size smaller. And for example, in an image, that might be removing some bits off every pixel. So we end up with an image that doesn't have quality that's as good, but it's smaller. Now, when we just get rid of those bits, they're gone forever. So we may end up with a smaller file size, but our compression is not reversible. And we can use lossy compression when it's okay to lose some data. So for example, with videos and images, we might not want to use lossy compression with something like an essay, because if we lose any words in the essay, then the essay doesn't make any sense, right? Now, the other type of compression is going to be lossless compression. And this is when we use an algorithm to reduce the file size. So we're actually not getting rid of any data, but we're still able to reduce the file size. This results in a file size for that particular file that's being compressed that is still larger than with lossy compression, but then still smaller than if we didn't use any compression at all. Because we're using an algorithm, this type of compression can be reversed. We use this when no data can be lost, for example, with text or software, which is made up of code, or something else where we really can't afford to lose any data. So as you can see right here, if you have an image with an original file size of 976 kilobytes, lossless, we might get down to 834 kilobytes. With lossy, we might get down to 212. But the trade-off for that is going to be the fact that we have a lower quality image. So you can kind of see how it's blurred. Okay, so now that we have a good understanding of lossy and lossless compression, let's look at some A-level questions. So here it says, a real-time video of a music concert needs to be streamed to subscribers. Take the most appropriate type of compression. And we could actually choose either one. There's a case to be made for either one, but then we need to justify it. I'm going to choose lossy just because I think that, first of all, especially if an event is running in real time, subscribers aren't going to care too much about whether you are losing some of the quality, which is what's going to happen in lossy because you're just getting rid of some data. And moreover, I would say that it would also take up less bandwidth, which means that there would be less buffering and you wouldn't have like sort of a disjointed experience of watching the concert. But let's see what the mark scheme says. So yeah, this is what I mentioned. I mentioned buffering as well. We actually need 3 points though, or we need 3 different reasons why. And I think the third one is that viewers may watch on different devices, so they may not need as high quality of resolution as would be given with, for example, lossless compression or without any compression at all whatsoever. Now, our next question, the photographs are compressed before they're uploaded to a web server. Customers download the photographs from this web server. Explain the reasons why compressing the photographs will benefit the customers. And I think this one is actually pretty straightforward. If you compress the photograph, it takes up less bandwidth to download, which means you can do other things while you're downloading an image. Additionally, I would also say it takes up less space on your computer if an image is compressed. And I think there are probably some other reasons. Yeah, also just overall, it takes up less time to download the photograph. So bandwidth, less time, less space on customer storage, and therefore the customer can store more images. Now we're going to cover one more concept here. And that's going to be something called run length encoding, which is just a form of data compression. And this is basically where consecutive repeated values are stored as a single value and a count. So for example, right here, if we have the values AAA, B, C, 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 then we would end up with A3, B1, C4 in sequence. Now A might have its own binary value. So instead of storing 3 different binary values, we just have the binary value for A followed by the binary value for 3, which would take up less space. We would do the same thing for B and for C. The binary value for C right here, and then the binary value for 4. And in that way, we'd end up taking up less space using run length encoding. Moreover, if we have an image, so right here, we're just kind of imagining that P is for purple and R is for red. But P again could be, the purple is going to be represented by some binary value. And then for example, for this whole row, instead of having 9 binary values representing purple, we might just have 1 binary value representing purple, and then we might just have a binary value representing 9. And we can apply this strategy to each row in this image, and we could therefore store the the color associated with each pixel in this image to using much less space than if we just took the binary value of every single pixel and we stored it that way. Now, the best way to understand this concept, I think, is by looking at some practice problems. Here it says a second bitmap image is stored using a color depth of 8 bits per pixel. The file is compressed using RLE, or run length encoding. And right here, we need to basically fill in this table in order to take the RLE compressed image and write what it would look like if it's uncompressed, and then vice versa. So here it says each color of the pixel in the image is represented by a hexadecimal value. And so complete the table. The first row has been completed for you. So presumably this is some pixels representing, or some values representing a row in an image, a row of pixels in an image. And if this is hexadecimal, this is going to be 4 bits, and this is going to be another 4 bits, right? Now, what we want to do is, again, as I said, take the uncompressed side, the uncompressed hex, and convert it to what it would look like if we compress the image using RLE. So right here we have EA. We just have one instance of EA in hexadecimal, so we can just write 1 EA. We have F1 twice, 2 F1, F2 3 times, 3 F2, and EA once, so 1 EA. So if you want to go the other direction, right here, we have the RLE compressed image. And so if you want to take this, we would just have AB twice. So AB, AB. We'd have FF twice, so FF, FF. And then we would have 1D once, so 1D. And then we'd have 6, 7 once. So just 6, 7. Now, if we had one of these 10 times, so let's say, for example, we had, I mean, that wouldn't happen in this case, but let's say we had like 1071. That actually, we probably wouldn't have 10 because this is all in hexadecimal. Instead, we'd probably end up having something like A71. So even the compressed values are most likely just going to be in hexadecimal, right? The 2, the 1, and the 1 right here. These are written as if they're decimal values, but remember, decimal values under 10 are the same in hexadecimal. So anyways, moving on, right here we have an uncompressed image, and we need to change it to RLE. We've got 2 instances of 32, so we can do 232. We have 1 of 80, so we can do 180. And then we have 2 instances of 81, so we could do 281. And that's going to end up being our answer. Just want to make sure, oh, right here I made a mistake. So it should be 2 Fs. So AB, FF, and then FF, and then 1D, 167. Or 1D, 67. So that's why I check the mark scheme. Sometimes I make stupid mistakes. Anyways, right here, another question. It says an image can be compressed using run length encoding. Explain the reasons why RLE might not reduce the file size of a bitmap image. Give one example in your answer. So I think a good reason why is, so basically if you look right here, RLE works because of repeating values, okay? So right here, we're taking up, for example, right here, we're taking up less space because instead of writing two hexadecimal values, F1 and F1. We just have 2 and then we have F1, which is going to take up less space, right? Now, we're actually, I think an even better example would just be this right here. This is definitely going to take up less space because presumably even if this is one hexadecimal value and another hexadecimal value, it's going to be less than 3. But let's say that we have all unique values, right? So let's say we have EA, F1, F2, and C3. So instead of just storing this, we would be storing one EA, one F1, one F2, and one C3. So instead of taking up the amount of space required for 4 hexadecimal values, which is just going to be, I guess, 32 bits, right? We would end up taking not only 32 bits, but also the additional space required for the numbers they're saying how often they occur. So if all of our pixels, for example, in a row and an image are unique, are different from each other, then RLE is not going to reduce the file size, but actually probably increase it. And if we look at our mark scheme right here, it basically says the same thing. And right here we have the example red, green, blue, and nothing is repeating, right? So we have red 1, green 1, and blue 1, which takes up more space than if we had just stored it as red, green, blue. Anyways, that brings us to the end of this video, and I'd like to finish off with some channel updates. So I'm continuing to work through paper 1. I took a bit of a break just because I started my new job, but I will continue to cover the topics in paper 1 until they're all finished. And as far as the programming sections go, I've kind of put this off for quite a long time. I think rather than just making a course, what I'm going to do is I'm going to solve individual paper 2 and paper 4 problems, and then release them on my channel, but only to members. And you can become a member by paying $2.99, I think it's $2 or $3.99 a month to get access to all the solved problems. Now, I haven't done this yet, but this is going to be coming soon. And I think this will be an easy way for me to approach this because rather than producing a large course, I can just release individual problems that don't take very long to solve and record one by one. Anyways, if you found value in this video and would like to see more like it, please remember to like this video and subscribe to the channel. Have a nice day.